Okay, once again, good morning to all. As we said, we will start with what are the things we are left over in the third module. Okay, so in third module, I think you might be remembering what we have done in few classes. We had few contact classes, and almost half of the portions we have completed. Okay, so we will start over with what is left in the third module. So what we studied in third module basically, we were deriving the field strength at a distance. Okay, we were deriving the field strength at a distance due to point sources. Okay, due to point sources, we have derived an array of point sources. We derived. Okay, so that only the continuation of those portions. Now we are going to see. And in addition to that, we are going to see the type of antenna arrays. Okay. I think we have completed the derivation of array of n isotropic elements separated by equal distance or separated by distance equal to lambda bit. I think we already completed that. Okay. So next we are going to see what are the type of antenna arrays, and after that we will see what is an inside array and what is a broadside array and general steps for the derivation of those things. Okay. I think you might be remembering we have derived unfair and broadside case or two isotropic sources. Okay, that derivation we have already completed within the contact classes itself. So here we will see the idea is same only. The basic things, basic ideas are same only. We will see how like we can apply it into a general case. Okay, or generalization of broadside and unfair cases, and the general steps we need to follow during the derivation. That also we are going to see in today's session. Okay. So first we will start with various forms of antenna arrays. Various forms of antenna arrays. So the various antenna arrays used are broadside array, unfair array, collinear array, and parasitic array. In this broadside and unfair array, I have already taken in the contact classes. Okay, then collinear and parasitic array, these two were left as assignments for you. I think you might have already written in your notebooks. Keep it ready with you. I may ask at any time. Okay. So this we will see one by one, and just refreshing the things. We can see first. We can see what is a broadside array. Broadside array. Broadside array is one which a number of identical parallel antennas are set up along a line drawn perpendicular to their respective axis. Okay. There is nothing but you can see in that pictorial representation itself. You can see these vertical things, shaded vertical things are antennas only. Okay, all that antennas are arranged parallelly, and the antenna array axis that is running perpendicular to that. Okay, so this is the arrangement of broadside array, and we have already discussed this thing. And the direction of maximum radiation, that direction will be perpendicular to antenna array axis. Okay, so that also you can see here the direction of maximum radiation. That arrow mark is there. That direction that is perpendicular to antenna array. Okay, and the direction of maximum radiation, it is bidirectional. Yes, it will direct or it will radiate towards both sides. That is perpendicular to antenna array axis means either it can direct in or it can radiate in this direction or this direction. Both these directions are perpendicular only. Okay. So this direction pattern is bidirectional. So the radiation pattern is bidirectional, because the only requirement is that the direction of maximum radiation should be perpendicular to antenna array axis. So that can be possible in two ways. So this radiation pattern we can say it as bidirectional, and this is the arrangement. Okay. In broadside array, individual antennas are equally spaced along a line, and each element is fed with current of equal magnitude, all in the same phase. Okay, this is the major thing you have to remember or you have to understand. Okay, here all the elements are equally spaced. Okay, and they are fed with current of equal magnitude and same phase. Their currents are having equal magnitude and all are in phase. Okay, here is the main difference. It is coming with the N-pair array. Okay, so that thing you have to understand. That is the only thing you need to understand in this. Okay. So by doing so, or that is by supplying currents of equal magnitudes, this arrangement fires in broad side directions. Okay, that means the direction is perpendicular to the line of array axis, where there are maximum radiations and relatively a little radiation in other directions. Okay, so hence the radiation pattern of broadside array is bidirectional. All these things just explained. The radiation pattern is shown here. See the radiation pattern. These dots are elements, okay, or antennas placed in the array. So they are placed like this. So that means these dots means they are projecting out of the screen. In that direction only, that antenna elements are placed. Okay, perpendicular to the screen. So the radiation pattern, how it will come? It will be perpendicular to the array axis. So this is the array axis. Okay. So the radiation pattern will be like this. It will be perpendicular. So the maximum radiation, direction of maximum radiation is perpendicular to array axis, and it is bidirectional. So this from the radiation pattern you can see that the major lobe is exactly perpendicular to the array axis. Okay. So the radiation pattern, and it is towards both sides it is radiating. Okay. Hence the radiation pattern of broadside array is bidirectional. And I have one question here. All of you please note down how the bidirectional pattern can be converted into unidirectional. I think I explained it in one class. I don't think I have explained it, this thing in both the classes. I think in EC1 or in EC2, I don't remember. I explained this in one class during our contact class session. Okay. So how this bidirectional pattern can be converted into unidirectional? That means I want an antenna array, a broadside antenna array, and its radiation pattern should be unidirectional. That means it should radiate in only in one direction. How that can be achieved? Okay, that is my question. You should write down the question, and you should find out the answers, and you should write it in your notebook. Okay, how the bidirectional pattern can be converted into unidirectional. So you have to write down the method, and then you have to write, or you have to draw the radiation pattern also. Okay, that is the procedure that I will be asking like at any time. Today itself, you can complete that. It is just a simple thing only. It hardly takes 10 or 15 minutes. Okay, today itself, you have to complete. From tomorrow onwards, I can ask at any time. Okay. So we'll move. Second one, that is end-fire array. This also we have seen. The end-fire array is nothing but a broadside array, except that the individual elements are fed in out of phase. Okay, usually 180 degree. So the individual elements are fed with currents of out of phase. In broadside array, the individual elements are fed with currents of in phase, okay, or same phase. Here, currents are out of phase. The individual elements are excited in such a manner that a progressive phase difference between adjacent elements becomes equal to the spacing in wavelength between the elements. Okay. So they are excited in such a manner that the progressive phase difference between adjacent elements becomes equal to the spacing in wavelength. Okay. This is lambda by 2 spacing. Okay, lambda by 2 spacing corresponds to which phase difference? Lambda is corresponds to 360 degree phase difference, and lambda by 2 corresponds to 180 degree phase difference. All these things we have seen, and we have done one derivation also based on this. Okay, so I'm not explaining much into that. So therefore, end-fire array may be defined as an arrangement in which the principal direction of radiation coincides with the direction of array axis. The only difference with broadside case is that here currents are out of phase. Okay, there will be a progressive phase difference of 180 degree between each elements. Okay, between the currents of each elements. So here what will happen? Instead of radiating perpendicular to the array axis, the radiation pattern will be coinciding with that of the array axis. Okay, that is the only difference here that we will see. See, here array axis is shown 1, 2, 3, 4, 5. They are the elements. Okay, they are placed in such a manner that they are projecting out of the screen. In that manner only they are placed. So their array axis will be as shown in the figure, that dotted line. And the direction of maximum radiation will also be in the same direction. Okay. So we can, just by seeing the radiation pattern, we can say an array is broadside or end fire. Okay. And the radiation pattern is also shown there. In that you can see the major lobe, the direction of major lobe is coincides with the direction of maximum radiation, or both are in the same direction. And there are some minor lobes also we can see. Okay, so that's all with broadside and end fire cases, which we have discussed already. Just we are refreshing the things. The third one is collinear array. What is mean by collinear? Collinear means they are in a line. Okay, so in collinear array, the antennas are arranged coaxially. That means the antennas are mounted end to end in a single line. Okay. Here, in a single line, antennas are mounted. I will show you just a practical picture of that. See, here you can see this is coaxial arrangement, or this is collinear arrangement. They are arranged coaxially. In the same axis only they are arranged, and they are in the same line. Here you can see like this only they are arranged. Okay, from in the same line only they are arranged. There are two types of arrangements are shown. So this is basically our collinear arrangement or collinear array. Okay, the individual elements are fed with equal in-phase currents, just as in the broadside case. Okay, they are fed with equal and in-phase currents. A collinear array is a broadside radiator in which the direction of maximum radiation is perpendicular to the line of antenna. Okay. Here also, just like broadside case, there we are using the term array axis. Here we are using the term line of antenna. Okay, line of antenna I have already shown in that picture. That is only the line of antenna, and their direction of maximum radiation is perpendicular to the line of antenna, just as in the broadside case. Since we are here also we are feeding with in-phase current only. Okay. And the gain of collinear array is maximum when the spacing between the elements is of the order of 0.3 lambda to 0.5 lambda. Or if it is falling within the range of lambda by 2, we can say it is less than lambda by 2 and near to lambda by 2, the gain of collinear array is maximum. That is just a point you need to remember in case if you are asked to write short notes on collinear array. Okay. The increase in the length of collinear arrays increases the directivity. Okay. If we are increasing the length of collinear array, it increases the directivity. So here two types of arrangements are shown: vertical antenna arranged collinearly and horizontal antennas arranged collinearly. The only thing is the antennas should be arranged in a straight line. Okay. And in the first case, in left side picture, you can see the axis of array is vertical, and antennas are arranged in that array only, vertically only they are arranged. So their direction of maximum radiation that will be perpendicular to that array axis. Okay. So direction of maximum radiation is marked accordingly. In the right hand side picture, there the same arrangement, but the arrangement is horizontal rather than vertical. The arrangement is horizontal. So antennas are placed horizontally, and the direction of maximum radiation is also shown accordingly. It will be always perpendicular to the axis of the array. Okay. So that's all with the collinear array. Here, that picture already shown me. Okay. So next, we will move on to parasitic array. Now, for all these things, you should try to understand the definition from the heading itself. From the name itself, you can understand. Okay, collinear means it's in a line. Broadside means it will fire towards the sides. End fire means it will fire towards the ends. So, based on those things itself, you can write at least 2-3 sentences regarding that. Okay. So, similarly, parasitic array. What is meant by a parasite? What is meant by a parasite? A parasite is an organism which lives on some other organism and feeds from that. Okay, it is feeding from some other organism. Okay. Similarly, here also we will show, we will see what is this parasitic array means in terms of antennas. Okay. In order to ease the problem of feed line, it is sometimes desirable to feed certain antennas of an array parasitically. Okay. Till now, we were feeding the antenna elements with currents. Okay. And for that, we are using feeding line. Okay. That is only antenna axis, array axis. Through array axis itself, we used to feed the elements with current. But here, that is very difficult to feed each and every element continuously throughout the array axis. So we are trying to do it in a different way. We are trying to feed antennas of an array parasitically. That means you will feed the current to some element of the array and the other elements will take from that particular element. The other elements will not be provided direct supply. Okay, they will take from some other elements. The element supplied power directly from source is called driven element. Okay, suppose we are having an array, in that one driven element will be there, that element will be supplied power directly from the source. And all other elements depending upon this driven element for getting their supply. Okay, so but a parasitic element is not fed directly. Instead, parasitic elements derive power by radiation from nearby driven element. So parasitic elements, how they are deriving the power? By radiation. The power radiated by the driven element will be used by the parasitic element. Okay, then how it is happening? That is next point explains how that is happening. Thus, parasitic elements obtain power through electromagnetic coupled with the driven element. These parasitic elements will be electromagnetically coupled with the driven element. So they are able to catch the radiation and accordingly a current will be produced in the in the parasitic element according to the changes in the driven element. So basically what will happen? If we are having a power supply, if we are having a current supplied to the driven element, there will be a parasitic element coupled with the driven element. And based on the changes of the radiations of the driven element, the parasitic element will draw current. Okay, since they are electromagnetically coupled. The amplitude and phase of the current induced in a parasitic element depends on its tuning and distance between parasitic elements and driven element to which it is coupled. Okay, that is the basic thing only. The current induced in the parasitic element depends on its tuning and distance between parasitic element. If the parasitic element is located at larger distance, naturally the induction of current or probability of inducing current will be less only. So they should be tuned properly to get maximum transfer. Okay, those are basic things. So here we are just introducing term reflector and director. Okay, a parasitic element lengthened by 5% with respect to driven element act as a reflector, and shortened by 5% act as director. So what is basically a reflector and director? A reflector reflects the electromagnetic waves. Okay, in antenna, so many elements will be there. Okay, antenna elements. In that itself, we can again classify that into reflector and director. Suppose a parasitic element that is having 5% length more than the driven element. Okay, then that is called as a reflector since it can reflect electromagnetic waves into other elements. And if it is shortened by 5%, it can act as a director or it can increase the radiation towards a particular direction. Okay, so that is only shown here. In the left hand side, you can see the reflector, okay, which is having more length compared to the driven element, and it can reflect the electromagnetic waves incidenting upon this to this direction. Okay, so the radiation pattern will be like this since the reflector is reflecting towards the director or towards the driven element. Okay, next is a director. Okay, here the driven element is this, and parasitic element or director is having a shorter length compared to the driven elements. So it can direct the electromagnetic radiation to this particular direction so that the radiation pattern will be like this. Okay, the parasitic array is of greater use at frequencies between 100 to 1000 megahertz. So I think you might have seen like what is a reflector and what is a director. This was there in the old Yagi Uda antennas. Okay, old Yagi Uda antennas, it was there. So I will just show you one picture of that. Okay, I will just. Okay, you might have already seen this thing. Meantime, I will take your attendance. Sorry. It's okay. It is okay. Sorry. Once again, I will do the presentation. Okay, can you see this? This is an old Yagi Uda antenna. In olden days, while that Trivandrum Doordarshan was there, now also it is there. But at that time, we used to use this type of antennas for getting terrestrial communication. Can you see this? Yes. Okay, in this, in left hand side, you can see 4 elements. Okay, 1, 2, 3, 4. 4 elements that arranged in a particular angle. These are reflectors. Okay, these can reflect the electromagnetic waves into these elements. These are reflectors. Okay, and these are directors. All other elements, they are directors. They can direct the radiation towards a particular side. Okay, this is a practical example of reflector and director. So again, we will go back to our PPT. So that's all with our parasitic array. So now we will move on to the design of broadside array. Basically, we want to study design of broadside array and endfire array. And this thing we have already done. Okay, we have already done this for an array of 2 isotropic point sources and n isotropic point sources. We have already done this. So this is general steps. I'm just explaining the general steps to be followed while designing a broadside array and while designing an endfire array. Okay, we will start with broadside array. Basic explanation, you know, an array is set to be broadside if phase angle is such that it makes maximum radiation perpendicular to the line of array. So this for maximum radiation. Theta should be 90 degree. Okay. Or the direction of radiation with respect to the array axis, that is only theta. That is 90 degree. So psi. What is psi? We have derived in all three derivations, we have already done the psi. Psi is the total phase shift. Okay, total phase shift. It is given as beta d cos theta plus alpha. Okay, and we are just substituting. We already have theta is 90 degree. Beta d cos theta means beta d cos 90. That is 0. So initially we are taking psi as 0. What is psi? Psi is the total phase shift at a distant point P. Okay. We require that should be 0. Then only we can achieve a good reception. So we are starting from the assumption that psi is equal to 0. And for that, what will be the value of alpha? That only we are going to see. And we already know that theta is 90 degree for broadside case. So we will equate psi, which is 0. Psi 0 equal to beta d cos theta. Theta is 90 degree. Cos 90 plus alpha. From that, we will get alpha is 0. Since cos 90 is 0, this term will become 0, which implies alpha is 0. Now, this is the basic step. First, we want to find out what is alpha, or what alpha is we want to find out. For that, what we have in our hand, we have for broadside case, theta will be 90 degree. That is we are having. Then we are finding out the value of alpha. Then we are finding out the direction of pattern maxima and pattern minima and major law of widths. Okay, these are the three steps we are going to do, even if it is broadside array or it is end fire array. Only thing is the value of alpha will be different and value of theta will be different for both cases. So here we are dealing with the broadside array in which theta is 90 degree. So direction of pattern maxima we are going to find out. I think you may be remembering this expression. ET total field will be equal to E naught into sine n psi by 2 divided by sine psi by 2. This is maximum. That only we are going to find out direction of pattern maximum. This is maximum means. Okay, do you remember this expression? We have done it around 2-3 times in different derivations. Okay, I think you remember. Okay, E naught is equal to sine n psi by 2 divided by sine psi by 2. Now we are going to find out direction of pattern maximum. So direction of pattern maximum means this should be maximum. This is maximum when numerator sine n psi by 2 is maximum. And there is one more condition, sine psi by 2 should not be 0. Okay, if sine psi by 2 is 0 means that is a point of singularity that we cannot do. Okay, so for that we are taking what is the maximum value of sine? It is plus or minus 1. Modulus we are taking plus or minus 1. Okay, so sine n psi by 2 is equal to plus or minus 1. All these steps we have done already. I think we are remembering. N psi by 2 is equal to 2n plus 1 into pi by 2. Since sine pi by 2 only is giving this plus or minus 1 quantity. Sine pi by 2 or 3 pi by 2 like that. Only odd multiples of theta will, or n psi, only odd multiples of 90 degree. Okay. Or only odd multiples of pi by 2 will give sine a value of plus or minus 1. Okay, and we will say n is equal to 0 corresponds to major law of maximum. That we already know, that is in 90 degree. Okay, n is equal to 0 corresponds to major law of maximum. Major law, since it is a broadside case, we know that is perpendicular with the array axis. There is no need to find out that. Okay, so we will leave that n is equal to 0 corresponds to major law of maximum. Or we will consider n from 1 onwards only. So just rearranging the equation, psi by 2 that will be equal to plus or minus 2n plus 1 into pi by 2n, or psi is equal to plus or minus 2n plus 1 into pi by n. Okay. So I think you will be remembering what is small n. What is small n? It is number of elements in the array. Okay. This n is an arbitrary constant. we just value varies from 1 to 3 like that. Okay, so just continuing that. So psi is equal to n plus 1 into pi by n. There are only these terms. So psi is what? Theta d cos theta plus alpha. So here we are going to find out the direction of parted maxima. Okay, for that only here theta max, direction of parted maxima. Theta max implies that only. Theta d cos theta max of what? Minor lobe. Since we already know the direction of major lobe. Major lobe is in 90 degree. So there is no need to find out that. So direction of parted maxima means it implies maxima direction of minor lobes. That only we are writing the notation like this. This you should remember, otherwise you will be confused like anything. Okay. Theta max means the direction of maxima of what? Of minor lobe. Okay. So cos theta max of minor lobe, just rearranging the equation, alpha will go this side, then just taking the cos inverse on both sides. So the equation will be reduced like this, where theta max of min is equal to minor lobe maximum. And for broadside area, we already know that alpha is 0. Just substitute that. Theta max of minor lobe is equal to cos inverse of 1 by beta d into plus or minus 2n plus 1 into pi by n. Okay. So this is a general expression. Okay. Now we want to substitute for each quantity. What is n? N is the number of elements. So up to here, this is a general procedure. After that, based on the number of elements and based on the distance between the elements, we can substitute values into this equation. Now we are taking, there are 4 elements only. N is equal to 4. And they are separated by a distance which is equal to lambda by 2. And what's the value of beta? Beta is 2 pi by lambda. That is everywhere, beta is that only. That we know already. So what will be the result? Substituting n is equal to 4, d is equal to lambda by 2, and beta is equal to 2 pi by lambda. What will be the result? Theta maximum of minor lobe is equal to cos inverse of 2n plus 1 divided by 4. Okay, this will be the equation, the final equation. Okay, so now what we can do? We can substitute each values for n. Okay, n equal to 0, that corresponds to the major lobe, that we already know. There is no need to put, or that is beyond the scope. N equal to 0, we should not put. Okay, the equation won't work because already we are having the assumption that n is equal to 0 corresponds to, is not assumption, that is reality only. Already we know that n is equal to 0 corresponds to major lobe direction, and we already know the direction of that also. It will be at 90 degrees. Okay, so if n is equal to 1, then theta maximum of minor lobe will be equal to cos inverse 3 by 4. That will be equal to plus or minus 41.4 degree and plus or minus 138.6 degree. Okay, these things already we have done. Okay, and n greater than or equal to 2 does not exist. Why? That also you should write it in your notebook. Why here we cannot put n equal to 2 or more than that? So just simple things. Okay, that also you should write in your notebook. What is the reason for n cannot be greater than or equal to 2 in this particular case? Okay, in this particular case, that also you should write it in your notebook. Now we are going to find out the direction of parted minimum. Procedure is same. We are writing the expression for total electric field. P equal to P0 sin n psi by 2 divided by sin psi by 2. Minimum means this value should be minimum, or this value should be 0. So sin n psi by 2 should be 0. Numerator should be 0, provided sin psi by 2 not equal to 0. Okay, this will happen if n psi by 2 is equal to plus or minus n pi. Okay, so n psi by 2 is equal to plus or minus n psi. That just we are rearranging. You will get psi is equal to plus or minus 2n pi by small n. Okay, same procedure. What is psi? Psi is beta d cos theta. Now we are going to find out direction of minimum or minor log minima. Okay, that's why we are writing it as theta min. Theta min of what? Minor log. Theta minimum means direction of minima of minor log. Okay, so beta d cos theta minimum of minor log plus alpha is equal to 2n pi divided by small n. Okay, now just what we did in the last step or in the last case, just rearranging the things to find out theta minimum of minor log. That is equal to cos inverse 1 by beta d plus or minus 2n pi divided by small n minus alpha. Okay, and we already know alpha is 0. Just substitute alpha is 0. We will be getting the general case for any number of elements and for any distance, means any distance between the elements or any separation between the elements. Okay, so that is the case. Theta minimum of a minor log is equal to cos inverse 1 by beta d plus or minus 2n pi by n. Okay, so next we are just giving the values. Okay, just giving the values. N is number of elements, that is equal to 4, and the separation is lambda by 2, beta is 2 pi by lambda, and we are putting n is equal to 1, and here we are putting n is equal to 2 also. Okay, here we are putting n is equal to 2 also. What can be the reason for that? That also you will you can understand if you already answered for the previous question. Because of the same reason only, here also we are putting n is equal to 2. Okay, or that is the same reason why here we are not putting n is equal to 3. Here they are saying n greater than or equal to 3 does not exist. Okay, that also you can write. Both the reasons are same only. If you are writing one reason, that is also the answer for this also. Okay, so we have already completed finding maximum direction maxima of minor log and direction minima of minor log. Okay, now we want to find out the beam width of major log. Okay, the angle between first nulls or double the angle between first null and major log maximum is the beam width of major log. It is denoted by the complementary angle gamma equal to 90 minus theta. Beam width of major log is given as 2 into angle between first null and maximum of major log. I will just explain what is that based on a picture. Okay, here you can see the first null beam width. Okay, first null beam width. Can you see the first null beam width here? Okay, first null beam width F and BW. That is, see here only. This is the direction of first null. First null means first 0. That is happening here, and in the right side also that is happening here. So this is giving a beam width. That is the first null beam width. This is only gamma, or this is the beam width of major log, or else we can say that this is the angle between first nulls, or we can say that it is the twice the angle between first null and major log maxima. Major log maxima is this direction. Okay, from here to here we can take the angle and we can multiply it into 2, or we can take the angle from here to here. Okay, that is only the angle between first nulls, or double the angle between first null and major log maxima. Okay, so it is denoted by the complementary angle 90 minus theta, and bandwidth between first null, it is 2 into gamma. Okay, so next we will move on to the derivation. Okay, we have theta minimum is equal to cos inverse n lambda divided by n d. That Okay, theta minimum of major lobe, okay, or minor lobe. That is equal to, sorry, minor lobe only. We are dealing with minor lobe only. Theta minimum is equal to cos inverse n lambda divided by nd. This equation, from where we are obtaining this? We are just substituting the alpha equal to 0 and beta equal to 2 pi by lambda in the general expression. Okay, and why we are doing like that? Because we want to get a general expression for theta minimum. Okay, beta is always 2 pi by lambda. Only things varies, which are things varies? N, number of elements, and D, separation between the elements. That's why we are substituting beta equal to 2 pi by lambda and alpha. Alpha you already know. Alpha is 0. Both the things we are substituting and we will be getting this equation, theta minimum. So you'll just put it is 90 minus gamma in order to find out beam width of major lobe. It is represented as complementary angle. So 90 minus gamma is equal to cos inverse plus or minus n lambda divided by nd. So just taking cos, okay, cos of 90 minus gamma. Here also we are taking cos of cos inverse, that will become n lambda by nd. Cos 90 minus theta, that is sin theta. So sin gamma is equal to plus or minus n lambda divided by nd. Since gamma is very small, yesterday also we have done one step like this. We can take sin gamma equal to gamma. Therefore, gamma is equal to plus or minus n lambda divided by nd. And first null occurs when n is equal to 1. Therefore, gamma 1 will be lambda divided by nd. Just substitute n is equal to 1. So bandwidth of first null, or beam width of first null, that is equal to 2 into gamma 1. That we already seen in the definition. That is 2 lambda divided by nd. What is nd? N is the number of elements and d is the separation between the elements. If we are multiplying both these together, what we will get? There are 10 elements and they are separated with 10 meter each. So 10 into 10, 100. What is that 100? That will be the total length of the array. Okay. So ND, we are representing it as the total length of the array, or L. Okay. So 2 lambda by capital L, or 2 by L by lambda radian. And in degrees, 2 into 57.3 divided by L by lambda degree. Radian, we are just converting it in degrees. So that will be like this. Here 2 gamma it is shown. Okay, and 90 degree major lobe, and 138 degree maxima of first minor lobe, and 41.4 degree maxima of minor lobe. This already we have done. Minus 138.6 degree, minus 41.4 degree. Here you can see maxima of minor lobes, and minima of minor lobes also you can see 120 degree, 60 degree, 60 minus 60 degree, minus 120 degree. Okay. Now, similarly, we are going to design end fire array. Okay. Here, all the procedure are same only except value of alpha. Okay. For an array to be end fire, psi is equal to 0 and theta is equal to 0 degree or 180 degree. Okay. Why theta is 0 degree or 180 degree? Since the direction of maximum radiation is parallel, or it coincides with the array axis. Okay. So theta is either 0 degree or it is 180 degree. It is not perpendicular. Okay. So we are taking it 0 degree. So psi is equal to beta d cos theta plus alpha. And we know theta is 0 degree. Cos 0 is 1. So psi should be 0. For better reception, psi should be 0. 0 is equal to beta d cos 0 plus alpha. For alpha is equal to minus beta d. That is the general case. Then we are going to find out the direction of pattern maxima. Et equal to E naught sin n psi by 2 divided by sin psi by 2. So this is maximum when numerator sin psi by n psi by 2 is maximum, provided all steps are same only, and we are going to find out what is psi. Okay, just go through the steps. Just go through the steps. Same step only. Here only one difference. We are substituting alpha equal to minus beta d instead of substituting alpha equal to 0. Okay. So just go through the steps. All steps are same only. So we are going to find out maxima of minor log. Okay, all steps are same. So theta maxima of minor log or minor log maxima. General expression we are getting it as cos inverse plus or minus 2n plus 1 into pi divided by beta dn plus 1. The only difference is here alpha is equal to minus beta d we are putting. Okay, and then now we are going to give values. Okay, n equal to 4. Number of elements n equal to 4. Separation between them lambda by 2. And beta is divided by lambda. Okay, and what that will give us theta maxima of minor log or minor direction of minor log maxima. That is cos inverse of 2n plus 1 divided by 4 plus. Okay, and here also n equal to 0 corresponds to major log maximum. Okay, so here n equal to 1 corresponds to minor log maximum. So n equal to 1, we are giving n equal to 1. So what will be the result? Just go through the steps. Cos inverse 7 by 4 does not exist. Why? If you are okay, I already asked the question for that. If you are writing the answer for that, you will be understanding this step also. Okay, so cos inverse 1 by 4, that is 75.5 degrees. Similarly, we are putting n equal to 2. Here also we are getting one more direction. Okay. Cos inverse minus 1 by 4, that is minus 75.5 degrees. Similarly, we are going to find out the directions of parted minimum. The steps are all same. Total field, you have to write them. Here, condition is n psi by 2 is sin n psi by 2 is 0, or n psi by 2 is plus or minus n pi. Okay. So, psi we are getting from that 2n pi divided by n. Same steps. Psi is beta t cos theta. Here, we are finding out minor log minimums. So, theta minimum of minor logs and alpha minus beta t. So, just go through the steps. We will be getting theta minimum is equal to cos inverse 2n pi divided by beta nd plus 1. Okay, this is the general expression. And now we are going to substitute the values. There are 4 elements and separation E is equal to. And once you are able to derive this general expression, you will be able to do it for any number of elements and for any particular distance. Okay, particular distance means any particular distance of separation between them. So here we are taking n is equal to 4 and d is equal to lambda by 2 normal basis. Okay, that you can do for any values. There is no problem. Based on the question you are receiving, you can do it for any values. So we will be getting theta minimum of minor log is equal to cos inverse plus or minus n by 2 plus 1. Now for n equal to 1, you will get direction of minor log equal to plus or minus 60 degree, and for n is equal to 2, you will get direction of minor log is equal to plus or minus 90 degree. Okay. So for n is equal to 3 and n is equal to 4, also we are getting values. This plus or minus 120 degree and plus or minus 180 degree. Okay. Next, we want to find out the beam width of major log. Same procedure we have to follow. Beam width of major log or BWFN is equal to 2 into angle between first null and maximum of major log. Okay, so cos theta minimum or cos theta minimum we are finding out from the general expression 2n plus plus or minus 2n pi divided by beta and d plus 1. And from that, we are just rearranging the things. Okay, so we will be getting 2 sine square theta minimum by 2 is equal to cos theta. We are rearranging it into 1 minus 2 sine square theta by 2. Okay, that is the only thing. And just substituting beta equal to 2 pi by lambda, we will be getting theta minimum is equal to 2 sine inverse plus or minus root of n lambda by 2 n d. Okay, for sine theta minimum, theta mean theta is minimum, so sine theta minimum is approximated as theta minimum, just as we did in the last case. So theta minimum, that sign we can avoid. Then what we will get? 2 into plus or minus root of n lambda divided by 2 n d. Okay. And just taking the 2 inside the root, 2 n lambda divided by n d. So beamwidth between first null will be equal to 2 into theta minimum. Again, we are multiplying this with 2. Okay, and we will get one time n into d in the denominator, that we will take as L. So for n is equal to 1, bandwidth will be beamwidth between first null, we will get 57.3 into 2 into plus or minus root of 2 by L by lambda d, or it is equal to 114.6 into root of 2 by L by lambda degrees. Okay, that will be the beamwidth of first null. Okay, likewise for an identifier array, the radiation pattern is also drawn here. Okay, they can see the radiation pattern, and you can just compare it with the radiation pattern of broadside array. Okay, so most of the things we have already done, and here the only difference was we are saying about a general case. Okay, we are saying about a general case. That was the only difference. So I think you might be remembering now. You might be remembering what are all things we have done so far in the third module. And today we have covered the general design procedures of endfire and broadside cases. Okay. So in the next class, we will be covering the remaining portions of the third module. Okay.